guess I should ask about Friday.
Yeah, so Friday, I think I'm going to give it maybe a 30% chance that we are canceled on Friday. Might be more than that. We just, every time they predict really heavy snow for us, we don't get any. So, who knows what's going to happen. I live 5 minutes from here, so I'm not apt to say, oh, I can't come in. But if we are having classes and you can't come in, like since you commute, then you can Zoom in and you can use that link that is the missing class link. And if you don't want to walk on the ice, that is perfectly fine. That is totally legitimate. So I get that as well. If we have classes that are canceled, I will probably email you with like a short video to watch, or a reading assignment. But I may just kind of hold up and do nothing since, we have some flexibility in the content that we cover.
She mentioned that you're planning to have a quiz Friday.
Oh, were we? Let's move that to Monday.
Okay.
So we'll leave the quiz where it is. Sorry, I was getting my weeks mixed up. But we're moving the test to the 18th.
For the test on the 18th.
Yes, but not on the 11th.
And the quiz will be over.
And the quiz will be over chapter 3. All right, so most of the stuff that I'm going to go over today isn't really anything new. It's just kind of more examples and kind of firming up stuff from chapter 3. And then I'll probably dabble a little bit into chapter 4. So on Monday, I had the junior seminar go over some Gen Chem topics. And so somebody was explaining intermolecular forces. Is that you all? Okay. No, that's why this was on here. So we've got some that are true for pure substances and some that are true for pure substances and mixtures. So our strongest one, we sometimes call them interparticle because an ion isn't really a molecule. So ion is probably the strongest. And above them all would be covalent bond. Now there are a few very weak covalent bonds, like the oxygen-oxygen bond is pretty weak, single bond. And the nitrogen-nitrogen single bond is pretty weak. But other than that, covalent bonds tend to be pretty strong. And I'm gonna erase this. So hydrogen bonding, we said, was between a hydrogen on one molecule and an electronegative atom on another molecule, and it needs to be a very small electronegative atom. So that was O, N, or F. So you can see they'll illustrated that with the hydrogen fluoride. So in pure substances, what this generally means is that you just have one of these bonds taking place. But if you have a mixture, for example, if you had HF and you had formaldehyde, this hydrogen could also be attracted to an oxygen that doesn't have a hydrogen on it. So it's just attracted to the electronegative atom. But the reason why being bonded to it is important is that when it is bonded to something that's very electronegative, this becomes more positive and that increases that attraction. Whereas if we compare hydrogen and chlorine, that bond isn't nearly as polar, and so the attraction isn't as strong. Now, generally in Gen Chem, we just kind of stick with this. There's a lot of literature that's kind of exploring hydrogen bonding similarities to things like having chlorine, so it's pseudo hydrogen bonding, or using lithium instead of hydrogen. or having a bond between a hydrogen-like bond between a hydrogen and a double bond. So have you guys heard the term olefin? An olefin is an organic compound that has a double bond. So if we think about the double bond here, we've got the sigma overlap like this, right?
There's quite a lot of electron density there.
Yep. And then we have the pi overlap. And the pi overlap happens with the p orbital sticking up.
Which one is this for?
We're still talking about hydrogen bond. Okay. And this is a pseudo hydrogen bond. It's not technically hydrogen bond. If I have a hydrogen, and let's say we're still attaching it to the fluorine here, and these have negative charges in them, this can be attracted to this region here. So some people would call that like a hydrogen bond because it's similar in strength, but another term for this is an agostic bond. So it's the same idea. It's not truly a sharing of electrons, so it's not truly a covalent bond, but it's stronger than polarity. And it can actually affect the shape of molecules. If we have, you know, the hydrogen thing dangling somewhere, it might be more strongly attracted to something changing bond methods and whatnot. So we'll come back to hydrogen bonding again in just a minute. What I want to do is go down to, so we had for our pure things, dipole, and then London dispersion. So if I have pure substances, those are my only possibilities. If I have mixtures, then I can have combinations of these. So in a mixture, the only ones I include are ions, dipoles, and induced dipoles. So if I have dispersion forces or hydrogen bonding in them, I would change hydrogen bonding to dipole and dispersion forces to an induced dipole. So let me give you an example. Let me get rid of the.
What kind of bond did you say was the?
It is an attraction between a hydrogen, like in a hydrogen bond, so it's attached to something electronegative like chlorine, and the pi bond. So it's not attracted to an atom, it's attracted to the pi bond. And I'm not going to quiz you over that right now, but it will come back later in the semester. So since we were talking about things that are similar. All right, I'm going to use a different color for my example because I think it's hard to see when everything's in the same color.
So you said mixtures have different bonds. Right? Is that what you're saying?
If I have a mixture and they have the same type of intermolecular forces, for example, if I had a mixture of H2O and ammonia, both of these have hydrogen bonding, so they would hydrogen bond with each other. So we would just call it the same thing.
Well, then they would also form ammonium hydroxide, so then yeah, you could be talking about ions.
Yeah. Try to keep it simple. Okay, let's do this. Water and methane. Keep it simple. Okay. If I have things that fit into different categories here, I'm going to list the stronger force first. So if I'm naming something that has a dipole mixing with an ion thing, I would say ion dipole because ion is stronger than dipole. And then if they have either a hydrogen bond or a London dispersion force, we're going to change those names because if the other thing doesn't have hydrogen bonding, generally you're not seeing hydrogen bonding. And we've seen there's some exceptions to that. But generally we would say the attraction is to the dipole. All right, so if I had water mixed with salt, putting them strongest first would be ion hydrogen bonding, but salt can't hydrogen bond with water, so we would change hydrogen bonding to dipole. And the dipole interaction with the ion is something you can do. So we can say ion dipole.
So is ion dipole stronger than hydrogen bonding?
It depends on the ions themselves. I would say generally probably because you've got a full charge rather than a partial charge. So,
But it's weaker than ion.
yes. So NaCl plus H2O becomes ion dipole. Okay. Not quite on the screen. And then we're going to change London dispersion. Capitalize someone's name. To induced dipole. So if I were trying to dissolve that salt in hexane, then I would call it ion induced dipole. Okay, so we might ask ourselves, why would nonpolar molecules be attracted to each other at all? Why aren't all alkanes gaseous, non-attracted to one another? When we know that octane in gasoline, that's a liquid. Why would that be a liquid at all if it's not polar molecules? So we're starting from the idea that the electrons are constantly moving around, but that motion is random. So we frequently have little areas, I'm going to call them pockets, of negative or positive charge. So the negative would be where the electrons are gathering more closely than would be random. The positive would be where they kind of abandon that side of the atom or the molecule and the nucleus is sort of exposed a little bit more. So we've got more of a positive charge. So this isn't permanent. With a dipole, like hydrogen chloride, that's permanent. That molecule is all the time polar. But in the case of London dispersion forces, this happens instantaneously. And we're talking like femtoseconds, 10 to the negative 15. Okay, so tiny, tiny amounts of time. Okay, so we call this an instantaneous dipole. Notice that it is similar to, but not the same thing as an induced dipole. Instantaneous. All right. And then as the electrons move elsewhere, then they're going to create their pockets of positive, negative elsewhere. And as they create these positive and negative pockets, the nearby atoms are also going to have their electrons shifted around momentarily. Okay? And so that's what creates that small little attraction. We can think of this as being kind of like a Post-it note. So the glue on a Post-it note, originally they thought they had failed at making a decent glue because it wasn't very strong, but it's strong enough to hold up paper, right? So even though it's weak in any given spot, if we spread it out over a big area, that's enough to hold up a piece of paper on the wall or something like So, it is weak locally, but I can increase the overall dispersion forces with two things. Since it's the electrons moving around, number of electrons, and with surface area.
You're increasing what?
The strength. So what this means is that we said all of these interparticle forces are going to affect things like surface tension and melting point and boiling point and viscosity. All of those things are going to be strengthened when we strengthen these interparticle forces. So we would expect that as we increase the dispersion forces, we should increase each of those properties. So before I give an example of that, something to remember that is often forgotten: everything has London dispersion forces. Yes. So water molecules are polar and have hydrogen bonding and have London dispersion forces. Sodium and chlorine in sodium chloride, they're ionic and they have London dispersion forces. It's just that all those other forces tend to dominate over the London dispersion forces unless I've got a whole lot of one of these things going on. Okay. So as an example, the trend is for heavier molecules who have higher, all of the properties, but I'm going to list melting point, boiling point. So if we look at our halogens, we know that they all bond the same way. I think I need to tilt this down. So the dot structures are going to look identical for all of those. If I look at the melting points, these are all in Kelvin. I go from 53.5 Kelvin, that's quite chilly, that's lower than the boiling point of liquid nitrogen, 171.6, 265.8. What can we say about that? How does that compare to room temperature?
Yeah,
It's about room temperature. Because room it's lower than what, 273.
What is 273? Is that room temperature?
Like 0 degrees.
That's 0 degrees. So it's below freezing, but it's pretty darn close, right, on the grand scheme. So this is below freezing, which means this melts below room temperature. And then if we were to look at the boiling point is above room temperature. And then iodine, where does that fit with room temperature? Yeah, this is quite a bit larger than room temperature. So this one is going to be a solid at room temperature.
And iodine is also kind of neat because it sublimates.
Right, yeah. It does have that unique property too. Okay, so we see this trend. So the trend for increasing size has less to do with the weight and more to do with the fact that we're getting bigger atoms, so there's more surface area, and overall there's more electrons. Yes.
When you talk about like the iodine sublimating, is there an instantaneous point in that process where the iodine is liquid and it just
No,
it just goes straight?
no.
to
When
sublimate?
there's something that's sublimating, it just goes directly.
Well, if you change the pressure.
If you
could,
change the pressure, you could do that, but if we're talking about sublimation, then that's not what
Then CO2 dry sublimates that, you know.
Right, but if you
atmospheric
have
pressure.
enough pressure, you can liquefy CO2.
Yeah.
Okay, so general trend to know is that as we increase the size, we tend to increase the melting point in the balloon. Okay, similarly, if we talk about surface area, and this also increases surface area, but this is going to give us a better example. If we take butane, which is, no, pentane, sorry. Pentane, which is C5H12, you end up with a boiling point of about 30 degrees Celsius. But this is if we have it out in, yeah, if we have it all in one chain, so in a long line. If we look at isobutane, which has that same formula, or isopentane. Oops. Should be CH3, 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 CH3.
It's neopentane.
Neopentane, thank you. So neopentane has all of those CH3 groups around the central atom. It's not as spread out. And this one has a boiling point of 10.9 degrees Celsius. Okay. So even though they have the same mass and the same number of electrons, the one that is a tight little ball instead of spread out has a lower boiling point. So that tells us that the forces are weaker, and the forces are weaker because as the molecules get next to each other, there are fewer points where they can influence one another. So if we think about a second normal pentane, and line up like this and get nice and cozy, almost like they're spooning, you know?
So.
But this one,
The neopentane is weaker.
these are weaker forces, okay? So with this one, the best I can do is get two CH3 groups together. Okay, so there's only just this one point of contact, whereas here, all of the electrons along the whole molecule.
Naked isopentane, we kind of somewhere in between the two.
So isopentane would be if we moved it, one of the methyl groups.
Yeah, and so it would kind of be between the two as far
Yeah.
as boiling point.
So what if you have like an aromatic like hexane versus like?
Okay, hexane's not an aromatic,
Sorry, I mean like
benzene.
benzene.
Yes. So yeah, aromatics tend to have higher boiling points than similar compounds that are not aromatic, because they have that
Flat.
layering that they can get those pi bonds interacting with one another. Exactly where I was going to go next, pi stacking.
So London dispersion forces was like the main thing responsible for like the increasing boiling point of heavier elements
Yes. Yeah.
as opposed to everything else.
Yes.
Learned something today.
There you go. Okay. So you can see this in several molecules, and I didn't think to look straight at benzene, but you might have heard of this with DNA. There's a phenomenon called pi stacking. This also happens with graphite, because graphite forms these vast sheets that are like a whole bunch of fused benzene rings. Okay, so with DNA, and I'm not a biochemist, so I'm probably going to get something wrong here, but you have your phosphate backbone, and then you have your nucleotide, right? Nucleic acid. Okay, so
not my area of expertise.
Now, you know, there's that, I think it's Huckle's rule that you can do, that you can count up the electrons and see how many joints there are and all of that, but I'm pretty sure that this is aromatic all the way around, but it's aromatic right in here. And so what this means is that all along here, each of these atoms, the nitrogens or the carbons, have pi bonds that are sticking perpendicular to the plane. So if I take this and tilt it so that I have looking on end here, there's the nitrogen, there's the nitrogen. Then I have a pi bond here, pi bond, or not pi, p orbital here, p orbital here, p orbital here, p orbital here, and that's what creates the aromaticity, right? They can all blend together there. But if there is another molecule either just like that or similar to it, so I think that it's adenosine and guanine that are similar. If we have this sitting here, thank you, I didn't see. Not a biochemist. I tend not to listen to what I'm saying, so gotta do better. So this also has p orbitals, and so that means that the p orbitals up here can have the same kind of London dispersion effect with the p orbitals down here. Okay. And so when you have a lot of aromatics, that can be a pretty strong influence. So we think of London dispersion forces as being very weak, but they can add up to a lot. So in that sense, it's a little bit like Velcro, where Velcro is weak enough that you can pull it apart. But if you have a whole sheet of Velcro, it can be kind of hard to peel the whole thing away from it.
Then like, if they're all in phase with each other, then you get that stacking, and it's sort of like resonance in a way.
Well, it's combining the resonance with the stacking here, but the idea of having the arrangement be just right and the angles be just right is definitely. All right, and it doesn't have to be DNA. That's just a common place where it's talked about. So I thought if you had biochemistry, you might have heard. Okay, so on Monday, we had started looking at hydrogen bonding, and we were comparing boiling points. So this is temperature, boiling points, and then this is molar weight. And if we look at something like the carbon group, the boiling point for methane is very low, CH4. And then the boiling point for silane a little bit higher. Boiling point for, I think it's germanium. Sure. And stannine. We get a pretty nice line, pretty much increasing in their boiling points, just like we did over here with our halogens. Okay, nothing unusual happening. But if I look at the next group over with the antimony, arsenic, phosphorus, and nitrogen, yeah, so these are polar instead of non-polar, so these are all going to be higher. So we have arsenane, phosphane. Oops, I skipped over something. This one's arsenane. This is probably stubborn. Okay, so we see that trend again, only
phosphine, arsine, stidane.
We see that trend is the same, but the temperatures are higher because it's polar instead of non-polar. But when we get to ammonia, instead of it being lower than others, it's higher. All right. So this was kind of what I was trying to illustrate on the board. I did it so rushed, I felt like it was kind of confusing. Okay. And let's see, I think it's actually even higher than that. That's pretty similar.
So why is the hydrogen chloride then right where the phosphorus, the BH3 is?
Okay. So this gets into statistics a little bit. If you're looking at the graph, you end up having the oxygen group kind of be up here, but then the halogens end up down in here where HCl is in here, right? And so the rationale that's usually given for that is that in pure HCl or any halogen,
It's just a small molecule.
I have one hydrogen that can be attracted to 3 different lone pairs here. And it's probably in any given situation attracted to more than one at the same time, but less than a full attraction, right? So there's 3 different lone pairs, but there's only one hydrogen to be attracted to. If I look at water, statistically, water has the same number of hydrogens as it has lone pairs. So that attraction, there's on average 1 lone pair per hydrogen. Everybody buddies up. And that allows for a stronger interaction. But if I go to the phosphorus group or ammonia, then I again run into this problem, but now I have fewer lone pairs compared to the hydrogens. So all of the hydrogens are sort of fighting for attraction to that same electronegative area of the atom. Okay. And so that's also why we see the HF is lower than that of water. Water is the highest of all of those. This one kind of goes like that. All right, so if you go through old quizzes and tests, I might ask something like, if you compare these 4 molecules, NH3, PH3, ASH3, SBH3, which one has the lowest boiling point? Okay, so first thing to remember is that the lower the boiling point, the weaker the forces. So we're looking for the thing with the weakest forces. And the dispersion forces, because they all have dispersion forces, the dispersion forces are going to be the weakest with the phosphorus. Because it's smaller, has fewer electrons. Why not the nitrogen? It's smaller, it has fewer electrons because it is hydrogen, okay? So it's important to remember that hydrogen bonding really does have a big influence on properties, starting with boron.
So if you were to go to the left of carbon, say, so like
to the boron.
To the boron group,
Boron.
would that follow
It
the
would look like this.
bottommost
Yeah.
one? So it only starts to have that trend once you start to get to nitrogen.
Right,
the
and then
oxygen.
notice these atoms, nitrogen, fluorine,
Fluorine.
oxygen. Those are the ones that are involved in hydrogen bond.
So it's just those three groups.
Yep. All right. So your book gives several examples of how hydrogen bonding is important, particularly in biological molecules. I talk about how when proteins are folding, the two forms that it folds into are the alpha helices and the beta sheets. Those are stabilized by the hydrogen bonding between the acid group and the amine group. And you definitely should all be able to draw a generic amino acid. So if I ask you about an amino acid, you should be able to say, okay, it looks something like this. I don't know what this last little thing is. That's the rest of the molecule, but generically it looks like this. So I've got hydrogen bonding here and hydrogen bonding here. And those attractions from one part of the protein to the next can create the structures of the helices or the sheets. This also is related to why water has the structure that it does when it forms ice. Is it stabilizes sort of this tetrahedral arrangement of the water molecules, and that kind of spreads them out compared to when they're kind of roaming around willy-nilly in a liquid form. So since they're spread out a little bit more, they're less dense, and if they're less dense, ice floats on water. So that's a pretty unusual property, even though it's like the most common substance that we ever think about is water, but everything else, well, almost everything else, a solid form would be more dense and it would sink.
Is that why you can have like a kilogram of ice and it'll melt it to less than a kilogram of water?
I know what you're asking, you said it wrong. The mass won't change, mass is conserved. Remember,
Right.
that's one of our first rules of chemistry. But if you had a liter of ice and then you melted it, you would have less than a liter.
But it's like when, in what weather, when like water seeps down into like stones and stuff, when it freezes, it expands and
Right,
it just cracks apart.
yeah. So the reason why pipes would bust would be because as the water expands, it's gonna break the pipes.
Yeah.
That causes erosion, like cracking sidewalks and things like that. The water gets into the cracks and it expands,
Yeah.
pushes it open. But also think about living cells. Most living things are made up mostly of water. So if you get something cold enough that you can freeze it,
You do a lot of damage.
yeah, you can do a lot of damage, particularly for animal cells, which don't have the cell wall to kind of stabilize that structure. You can start tearing apart the membranes of things. So
A lot of times.
frostbite is actually when we have it cold enough that we're starting to tear apart those cells with the ice.
A lot of times, it's severe frostbite, limbs like turn black, you have to amputate.
Exactly. Yeah. Okay, so where are we on time? Oh, we have 3 minutes. Okay. What I want you to do, whether or not we have class next week. Well, first of all, I did finally post homework 3, and that's going to be due Wednesday. So you have plenty of time to look at it, and you can ask some questions on Monday if you need to. Hopefully we'll be here on Friday and you can ask some questions then. Otherwise, ask them on Monday. So homework, not homework, homework 2, chapter 3.
Is that like to turn in or?
It's on Canvas. It's due Wednesday. Several of the questions I just put into one thing, and it's drawing dot structures. So you'll write them out and then just take a picture of everything you did. And if you want to, you can just like answer all of the questions on a sheet of paper and upload them. I'm fine with that too. And it'll grade it as a 0, but when I see your work, I'll go back and put in the points for the other things. But I want you to be looking at symmetry operations. There's only one here, right? Or is it 2? I don't know.
This one.
Symmetry operations. This is chapter 4. So you need to know what is a symmetry operation. And then you'll be looking at like an axis, a point, and a plane that we have the symmetry operation going around. So what I want you to know are those symmetry elements and symmetry operations, kind of have a sense of what that means. And we'll talk about specific examples and what all of the labels are. But next time we meet, I want you to understand those terms. If class is canceled on Friday, I will try to be on the class Zoom, at least for the first 15 minutes of class, so that if you have questions over homework, you can just check in with Zoom and ask me questions that way. But if nobody shows up after 10 or 15 minutes, then I'll log.